Welcome back to The Explainer. Today, we are diving into two really powerful tools that economists and researchers use all the time: difference GMM and system GMM. You know, when your data has a memory, when the past influences the present, picking the right method is absolutely critical. And we're going to break down exactly how you can do that. So here's our roadmap for today. We're going to start by really getting a handle on what it even means for data to have a memory. Then we'll meet the first clever solution to this problem, difference GMM, and you guessed it, we'll see where it falls short. From there, we'll introduce its smarter, more powerful sibling, system GMM. And this is the most important part. We'll walk through a super practical test to help you choose between them. And finally, we'll cover how to double-check your work to make sure your conclusions are solid. All right, let's kick things off with the big idea at the center of all of this: data with a memory. Now, in statistics, we have a fancier word for this. We call it persistence. It sounds pretty intuitive, right? The past affects the present. But as you're about to see, this simple concept can create some massive headaches when you're trying to analyze your data. To put it simply, persistence just means history matters. What happened last year has a real impact on what's happening this year. And the stronger that persistence is, well, the more weight the past carries into the present. So you might be thinking, what's the big deal? If history matters, isn't that just useful information? I mean, if a company's profits last year help predict its profits this year, great. But well, from a statistical standpoint, it's a lot trickier than it looks. The issue has a name, and it's a real tripwire for researchers: endogeneity. The best way to think about it is that our variables past is all tangled up with a bunch of other hidden things that we just can't measure. And when that happens, our standard statistical models just break. They can give us results that are not just a little off, but completely wrong. So how in the world do we untangle this mess of endogeneity? Well, this is where our first hero of the story comes in, a technique that was specifically designed to fix this exact problem. Back in the early 90s, two economists, Manuel Arellano and Stephen Bond, came up with a really brilliant method called difference GMM to deal with this issue, especially in what's called panel data. And it's a really clever two-step approach. First, it differences the data. So instead of looking at, say, a company's total profit each year, it looks at the change in profit from one year to the next. This little trick cancels out a lot of that hidden, unchanging stuff. Then, for the remaining mess, it uses data from the more distant past as what we call instruments. You can think of them as clean, reliable stand-ins to help us get an unbiased answer. But like a lot of first solutions, this one has a kind of Achilles heel. It's a fantastic tool, for sure, but it doesn't work perfectly in every single situation. And here's the real irony. The very problem that difference GMM was designed to solve, that strong persistence, that strong data memory, is also its biggest weakness. Researchers found that when a variable's memory is super strong, especially over a short period of time, the tool itself can start to give you biased results. So here's the bottom line. When that data is super persistent, those past values it tries to use as instruments just aren't very good predictors anymore. They become weak, and that leads to unreliable results. On top of that, that differencing trick we talked about, it completely erases any information about things that don't change over time, and it has a tough time with messy, real-world data that has gaps in it. Now, these weaknesses didn't signal a dead end. Not at all. Instead, they actually sparked an evolution in thinking, which led to a much smarter and way more powerful solution. And here's the key upgrade. Instead of only looking at the change in the data, the way difference GMM does, system GMM does that, plus it looks at the original data, what we call the levels. It's a two-equation system, and that means it uses a whole lot more information that was previously just being left on the table. And the payoff for this approach is huge. By using more information, system GMM can bring in more instruments, which means you get more precise, less biased estimates. It's also way better at handling that messy data with gaps, and, this is a big one, it doesn't throw away all that useful information about variables that don't change over time. Okay, so now we've got two tools in our toolbox, the original model and the upgraded one. So how do you, as the researcher, know which one is the right fit for your particular data set? Thankfully, we don't have to just guess. Stephen Bond came up with a really practical diagnostic test that gives us a very strong clue about which model we should be using. And the test is actually surprisingly straightforward. It's just 3 steps. First, you run a basic OLS model. This is going to give you an estimate that's almost certainly too high. That's your ceiling. Second, you run a fixed effects model. This will give you an estimate that's probably too low. That's your floor. So now you've got a range where the true answer should lie. The last step,
You run your difference GMM model and see where its answer falls.
So the logic is really simple. The real true answer should be somewhere between that high OLS number and that low fixed effects number. As you can see here, this creates a kind of valid zone for our result. So the million-dollar question is, where does our difference GMM estimate actually land? Inside the zone or outside?
In this example, our difference GMM result was 0.42. Well, that's below our floor of 0.44, and that is a classic red flag. It's a huge signal that our difference GMM estimate is probably biased downwards because its instruments are weak. And that tells us pretty clearly that system GMM is the better, more reliable choice for this data.
Okay, so you've run the test, you've picked your model, but hold on, you're not quite done yet. There is one last absolutely crucial step. You got to do some quality control to make sure your results are actually trustworthy. There are two main hurdles you need to clear. The first is called the Hansen test. It basically asks, hey, are those instruments you used to fix the problem actually valid and doing their job correctly? Here, you're looking for a high p-value. That's a good sign. The second one is the AR2 test. This checks for any weird leftover patterns in your results that might be a sign of trouble. And again, a nice high p-value tells you you're in the clear.
So, there you have it. From figuring out you have a data memory problem, to choosing the right tool for the job, and then finally checking your work. The GMM framework is just an incredibly powerful way for us to understand exactly how the past shapes the present. And it reminds us that in our data, just like in our own lives, history really matters. Which leaves us with a pretty cool question to think about. What powerful patterns from the past are quietly shaping your world right now?